Hello, good afternoon. So today we were discussing rotational dynamics. It's Newton's second law for rotation. Newton's second law previously is F equals ma, right? So it's telling us the force acting on an object, add up all the net forces, is equal to the mass of the object times the acceleration of the object. So for Newton's second law for rotation, acceleration becomes alpha. So linear acceleration becomes angular acceleration. Force becomes torque, okay? And mass becomes rotational inertia, okay? So we have already discussed what alpha is, right? What the definition for alpha is. Today we're gonna study torque. And then after we've discussed torque, we can look at rotational inertia, and we can put everything together to have Newton's second law for rotation. So torque equals I alpha. So just like how force generate linear acceleration, torque generate angular acceleration. So for example, now if you have use this wrench, try to loosen this bolt here, right? You wanted to give it, you want to make this to start rotating. It was not rotating before, and it starts to rotating, which means you wanted to give it an angular acceleration. So it starts rotating, pick up some angular speed. So you need to give it a torque, right? There are different ways to apply this torque, and some of the forces will generate a large torque. Some of the forces will generate a smaller torque. So imagine that if you push this handle from this side, are you going to make it rotate? Probably not, right? And you need to apply the force over here, make it rotate this way, or you can make the force there, then it will start rotating the other way. So, and also, if you put your hand over here, that's going to generate a smaller torque. If you put your hand over here, that's going to generate a large torque. So that's what we call the level arm. Level arm, longer the level arm, the bigger the torque that you are going to generate. So level arm also matters. So torque, you can see that the level arm, the distance where the force is applied matters. And of course, the amount of the force you are applying also matters. Also, the angle, at what angle you're applying this force also matters, right? Because if you apply a force over here versus if you apply force, you're pushing this thing, you're not going to generate any torque. So it turned out the torque is R times F times sine of phi. Phi is the angle between R and F, okay? So if you have 90 degrees between R and F, that's going to give you the maximum amount of torque possible. If you have 0 degrees, like if you push toward the center of the rotation, then you're not going to have any torque. So that's an angle, sine of 0 is 0, sine of 90 degrees is 1. Okay, so level arm matters, the amount of force matters, the angle between your level arm and force also matters. So it turned out all of this will affect the amount of torque that you generate. Okay, so we can also take a look at that by looking at this demo.
Torque is a turning force, and the torque.
Every resolution starts with the right routine and the right equipment, like Casper's Wave Hybrid.
Torque is given by this Greek symbol tau. It's the product of the force magnitude and the lever arm, which is a distance measured in meters. So what I'm going to do is I'm going to hand this T-shaped piece of wood to my able assistant Parker, who will grip the wood with his hands. Then I have some hooks here to which I will attach this mass at different locations. So the torque exerted when I attach the mass here will be less than the torque exerted when I attach the mass, say, here. The axis of rotation is here. Parker will be attempting to prevent this T from going down. And as I attach the mass at farther and farther points from the axis of rotation, the torque will increase because the lever arm is increasing. So let's have a try here. See how tough Parker really is. No problem. A lever arm of maybe 20 centimeters. Again, not bad. Not bad at all. And he's starting to strain. That's the best I've ever seen anybody do it. So give a hand to Parker. And but Parker, report to us, what was the difference? The mass was the same, but what was the difference?
It gets harder the further it is. It'll start twisting down.
Because the turning force, that torque, is increasing as we increase that lever arm. Perfect.
All right. So quickly, this demo is showing us increasing the lever arm, which here is represented by R, increase the torque. Obviously, if the professor had used a heavier weight, that is increasing the force. So the turning force in this case is the torque generated by the weight of the gravity of that weight that he was holding, right? So that is the torque, and the person holding the bar is trying to counterbalance that. The bigger the torque is, it is harder for the student to hold. But also we realize that torque is a vector, so we need to be able to take the signs into account. So if you take a look at the units for torque, you probably have already noticed it's Newton times meter, right? But we say it's not joules because joules will represent, remember, energy. It also represent work. Both of those quantities are scalars, but torque is a vector. So we're going to keep the units for torque, Newton times meter. We're not going to write joules, okay? So it turned out in order to also take into account the vector sign for the direction for the torque, we can rewrite this relationship using a cross product between R and S, okay? Because the cross product give us the sign of the angle. So you may have already come across how to do cross product in your math class, but if you haven't, no worries. We're going to go through this piece of math together in this context of torque. You probably still remember how we do dot product, right? So you can multiply two vectors in two different ways. You can do a dot product, a dot into B, that give you a scalar. And if you can do A cross B, that give you another vector, okay? A dot product is when we do calculation work, force dot into displacement, F dot into dl, that is a dot product. Here is a cross product, R cross F give you the torque. Okay, so a little detour to see how to do the cross product. Okay, if you have A and B, so A and B forms a plane, the third vector C as A cross B is going to be perpendicular to the plane. So this is your C. Okay. The magnitude of C is A times B, A, the magnitude, B, magnitude times sine, C, the angle between A and B. Okay. And we can use right-hand rule to do this cross product. So let me show you how to do the right-hand rule. Right-hand rule means that we never use our left hand, so make sure that you don't use the wrong hand. There are two different ways to do right-hand rule. So I'm going to show you the first way. First way is you take out your forefingers, your right hand, and let your forefingers to point in the direction of the first vector. In this case, I'm using A cross B. The first vector is A. So my forefingers is pointing in the direction of A. As I'm looking at my screen, I'm aligning my forefingers in the direction of A. And where is B? B in this case is towards you guys, is in this direction. So I need to curl around my finger to where B is. So curling around where B is. And thumb gives you C, that is A cross B, the direction of C. Okay, so C is perpendicular to both A and B. Okay. When you see that, as long as A and B are in the same plane, it doesn't really matter which C direction. A and the angle between A and B can be bigger or smaller that give you the same C that's perpendicular upward. That's the first method. The second method is to form a sort of XYZ axis using your three fingers. So X and Y, Z, those three axes are following the right hand, right? So I'm going to use your index finger pointing in the direction of your first vector A and your middle finger to pointing in the direction of B, second vector. And again, your thumb points in the direction of C, which is the cross product between A and B. So whichever way you like, sometimes you may be harder to rotate your hand to be aligned the way you want. So you have to choose whichever method feels most comfortable for you. So there are some rules for the product, cross product. You can see if you switch the position A and B, it will switch the direction. You need to come up with a minus sign. So A cross B is minus B cross B. If A and B are perpendicular, which means they have a 90-degree between them, right? A cross B is going to be A magnitude times B magnitude because the sine of the angle is 90, sine 90 is 1. A and B are in the same direction, then the cross product becomes 0. Okay? Those are simply derived because of from the definition. Let's do a quick check-ins with your understanding of the cross product. So in this XYZ or I hat, J hat, K hat, we're looking at what is J plus I plus K hat. Feel free to take out the right hand and do the right hand roll if you wish. What is J plus I plus K? Okay, all right. So I gathered majority of the vote. So let's run the clock for 10 more seconds. If you haven't voted already, 10 more seconds. Okay, any last minute vote? Okay, so if not, I'm going to go ahead and close this. All right, so this is our results. Okay, so to do the addition, first we have to do the cross product between J hat and I hat. So J cross I, anybody would like to tell us what do we get for J cross I? So I'm gonna do the first method, okay? The first vector is J hat. So 4 fingers pointing toward the J direction, which is the Y direction to the right, and X is toward me. So I need to curl around my finger towards myself, toward me. And my thumb points in the direction of this cross product, which is downward. So what is J cross I? What did I get? Is it K hat? It's opposite of K hat, right? It's negative K hat because K hat is upward. So this one gives me negative K hat plus K hat. I get 0. So the correct answer should be A, 0. Now, if it were I cross J, you see I is this way, I is my X, J is to my right. If I do I cross J, I get K. Okay, so if I do I cross J plus K, then you would choose B, and that would be the correct answer. But since it's J cross I, that is negative K. right? So just be a little bit careful of which one is dot into which one. Yeah, so the first variable is the 4 fingers where I start my my right hand on. So this is a checkpoint question that you have already done. Again, we are looking at torque. Right? 2 different cases. Case 1, you have a force applying here midway through the bar at a distance L/2 away from your center rotational axis. The angle between these two, between the bar and the force is 90 degrees. Case 2, you make a 30-degree angle, but you apply it at the end. So how do we compare the torque? Okay, let's look at the definition of the torque. The magnitude is R times F times sine phi, the angle between them. Okay, the R is a vector, is pointing from the origin, center of rotation, to where the force is being applied. So in this case, this is my R. Okay, this is my R. So, okay, and the angle is between R and F. You can see the angle between them is 90 degrees here. So R here is a magnitude is L/2, half of the length, times the force times sine of 90 degrees, which is 1. And I get 1/2 F times L, right? That's the torque in case 1. Now the torque in case 2 is R. So it's R1, this is R2, F sine of phi, phi1 and phi2. So this is R from your axis of rotation to where the force is being applied. This is your R, and this R is L. The same force, now sine of 30 degrees. Sine of 30 is 1/2, so you get 1/2 F times L. You can see that these two cases give you the same torque, even though that the force is being applied to different location, because one of them is applied at a shorter distance but has a bigger angle, or one of them is applied at a longer distance but smaller angle. So overall, they give you the same torque. Okay. So really just a direct practice on using the definition for torque. Definition for torque is R cross F, which is RF sine phi if you look at the magnitude. Okay. Okay, now let's look at another question. Which of the 4 forces produce a torque that points in a z direction? So through this question, I want to show you guys sort of a shortcut of figuring out the cross direction of the cross product. So here, if you want to figure out which one of these have a torque in the z direction, obviously you can do R cross F. You can draw the R and you can draw the F and you do the cross product. For example, here this is F4, right? This is where the force is applied. This is the center of rotation. This is my R, and you can extend this R a little bit further. This is your R, and this is your F. And you can do your cross product and to see which direction is pointing at. But I want to show you more of a simpler method is whichever the direction. So you can see it is rotating according, the axis rotation is in the z, right? So the positive z direction is corresponding, remember we were saying, how do we do angular velocities? The direction of angular velocities is a counterclockwise rotation is pointing in the z direction, okay? So if this force is pushing the wheel counterclockwise, that means it's going to be in the z direction, right? Clockwise, it gives you a negative z direction. So try to use that, but simply that oftentimes it's easier than to do the cross product. All right, so I'm going to give you a minute or two to discuss this question, and then when you come back to it.
Professor Ryan,
Yes.
I just have a quick question before I go to my breakout room. Are you gonna have office hour today after the class, or?
I don't have today, but next Wednesday we have our office hours.
Oh,
Perhaps I'm going to have an extra one on Monday, but I'll send out details, okay?
okay. So, because I wanted to talk to you about my situation with the flipped physics. So, can we talk about it after the class, or do you want me to wait till Monday to talk about it?
Why don't you send me an email to see if I can resolve it in the email, because I do need to go somewhere after the class. So
Oh,
why
okay.
don't you send
Yeah.
me an email? And then if you could not resolve it in the email, I'll talk to you on Monday.
All right. Sounds great. Thank you very much.
Sure, no problem.
All right.
All right, 10 more seconds if you haven't voted already. 10 more seconds. All right, any last minute vote? All right, I'm gonna go ahead and let's take a look at this. I'm gonna go ahead and close it. All right, so let's look at F1, for example. So F1, do you think F1 will generate a rotation? If so, in which direction will it rotate? So F1 is like where you're trying to unscrew that bolt by pushing through the center. You're not going to have any rotation by pushing through the center. You can also see this by looking at R and F. So R is from where the center of the rotation is to where the force is being applied. So this is your R. You can see R and F are in the same direction. So R plus F is going to be 0, right? Because the angle between them is 0. So you're not going to have any torque. So the same way goes for F3. It's not going to give you any torque if you're pushing toward the center of the rotation. How about F4? F4 is going to push it. It's going to rotate clockwise or counterclockwise.
Clockwise.
Clockwise, very good. So F4 is give you a negative z hat for rotation, for the torque. F2, you can see that it's going to push it counterclockwise, right? So F2 is going to give you a z direction for rotation. So B is correct. Very good. Okay, so this is a question, I believe is one of the homework questions. So we can use this as an example to see how do we calculate torque. So you have various different forces. I want to calculate the torque of various forces. So the first question is, what's the magnitude of this torque due to F1? Okay, so F1 is over here. The force is applied at here, and center of rotation is here. From center of rotation to F1, this is your R, right? So we do, for the first question, we do torque is R1 cross F1. If you want to look at the magnitude of this, is going to be R1 F1 sine of 90 degrees because they're perpendicular, right? R1 is the radius, is how long this is. So you're going to put R and F1 times sine of 90, which is 1, okay? You can plug in the numbers later, times F1 is 333 newtons, which is 455 Newton times meter. Okay, so that's the first question. Second one, what is the magnitude of the torque on a disc due to F2? And you can see F2 is exactly applied toward the center, right? You know that's not going to give you any torque. And also the distance from the R is from here to here. This is R. R and F are in the same direction, so you're not going to get any torque, so 0. What is the magnitude of torque of F3? F3 is here. Okay, so this is where the force is applied. This is your center of rotation, and again, R is from your center from your axis of rotation to where your force is being applied. So this is R3. So the angle between F3 and R3 is this angle. And this angle is 54 degrees. Okay. Because it's telling us this force is acting at the edge of the disk at an angle theta 36 above the x-axis, which is above the x-axis. So which is this angle, right? So this is x, this is 36 above. So this is 36, but we want this angle. This angle is the same as this angle, which is 90 degrees minus 36, 54 degrees. So this is the angle between R3 and F3. So the third torque is going to be R3 F3 sine of 54 degrees. Okay. And R3 is again the radius. F3 is 337 degrees, and you can calculate the torque. Newton meter. And in terms of the direction, so here it doesn't really ask you the direction, but in terms of direction, again, we can use the which way it's rotating. F1 is going to make this disk rotate counterclockwise. That's a positive z direction, right? F3 is going to make the disk rotate clockwise, and that is going to be a negative z direction. Okay, so you can use that which way it's rotating to quickly figure out the direction of the torque. All right, next 3 questions. What is the x component of the net torque on the disk? The x component. Well, you can see that the torque we just calculated all in the z direction. So, which means it does not have an x component. The torque is not going to make the disk rotate relative to the x-axis. It's always rotating relative to the z-axis, right? So the x component obviously is 0. The same way goes for y, okay? Because all the torque is in the z component. So you simply, by asking the z component, it's really just asking the net torque. All the torques, to add the torque due to F1, due to F2, due to F3. This one is 0. This one is positive. We just calculated 455 in the z hat. This one is negative 368 in the z hat, negative z hat. So that's your net torque, which is about 87 Newton meter in the z hat. Okay. Okay, so that's just again a direct application of the definition of using torque, right? Which is R cross F. So any questions about this particular problem? Any questions? Any questions? Okay, now let's talk about rotational inertia. We did, so in terms of Newton's second law for rotation, torque equals I alpha. We have done alpha in our previous class. We just did torque right now. Now let's discuss I. So I is the counterpart of mass in rotation. And why is not mass? So because think about this, this is like the mass is really, we have this term of inertia describing sort of when you want to, this is sort of describing, it's an outdated term, but historically inertia used to describe how hard it is to accelerate something, right? The bigger the mass is, the harder for you to change the status of the motion. So rotational inertia is sort of the same idea, how hard it is for you to change the rotational status of something. So let's try to derive what the rotational inertia for a point mass by looking at, okay, if you have this mass that is rotating around the center axis at a radius r, the entire string, and on the other side of the string you have a mass, you simply start rotating with angular velocity omega. What is the kinetic energy of the mass? Okay, so the kinetic energy is 1/2 mv squared. We know that from previous knowledge. But in this case, the kinetic energy, the v is your linear velocity, can be related to angular velocity by radius r. V is r omega. Still remember that from our previous class? So here I'm going to plug v using r omega. So r is this radius, capital R here, r omega. And you can see that if I'm forming a rotational kinetic energy in a similar format of 1/2 some quantity, instead of a linear velocity, I have angular velocity. Whatever comes here should tells me the counterpart for me where mass is, so the equivalent for mass. You can see that if I have make this into 1/2 something omega squared, the rotational inertia is mr squared. So mr squared is what we're going to call the rotational inertia, which is what used to be described by mass. Here we use rotational inertia to describe it. Okay, mr squared. So this describes how hard it is to rotate the mass. You can see that in order to rotate this mass, not only the mass matters, but also the radius away from the center matters. The longer you extend this mass outward, the harder it is to rotate it, right? The shorter the distance, the easier it is to rotate it. So both the mass and the radius should matter in terms of how hard it is to rotate. And we're gonna call this quantity rotational inertia. This is just for a point mass, right? Like a point particle. Okay. So we have found rotational inertia for a point particle and the rotational inertia for a different shape, right? So if you have many collections of point particles, so for example, instead of rotating a 1 point part, you rotate 2, then you need to add both of them together. So you add the mass and r squared together, do a summation, and that's a rotational inertia. But instead of one discrete object, you have a continuous distribution. Imagine you have many dots connected, right? So that give you like a long bar. It's a continuous distribution. Then you need to do using integrals. So instead of adding a little bit of mass, each of the mass is now represented by little dm. You're integrating over the r squared times dm. Okay. But luckily in here, we never really had to do all of the calculation from scratch. The usual shapes that there is, like a disc, like a sphere, like a cylinder, all of these, like a hoop, all of these rotational inertia that's already been calculated. And what we need to do is we simply just use the formula. Okay. Rotational inertia have another name called moment of inertia, just so you know that it can be referred to another name. Okay, so let's look at this checkpoint question you have already done. This is a triangular shape. This entire object consists of 3 point particles, right? 1, 2, 3. They're connected by massless rods, which means you don't have to think about rotational inertia of the rods. You only need to think about these 3 masses. So the rotational inertia, or the moment of inertia of this entire object relative to, if we're rotating relative to A, or rotating relative to B, or rotating relative to C, they all have different rotational inertia, IA, IB, or IC. So which of the following order is correct? Okay. All right, so rotated relative to A. Imagine if this one has a little handle where you can hold. You try to swing it around, or if you can have a handle here or handle here. Do you have any intuition on which one is most hard to rotate? That kind of intuition is good, help you understand the rotational inertia is relevant to both mass and distance. Do you have any intuition? If you hold your handle at A or B or C, which one is harder to rotate? Anybody?
At A?
Point A. And why do you think that is?
Because it has the most mass at the farthest point.
Yes, very good. I like that you described that in one sentence, have the most mass at the furthest point. So let's see how we actually calculate the rotational inertia for all 3 different situations. So let's do A. So is M, I'm gonna call 1, 2, 3, okay? Rotational inertia is the sum of mr squared, which is going to be m1, r1, m2, r2, m3, r3 squared. So if you're rotating relative to A, obviously R1 is 0, because 1 is at the rotation. It has no distance from this axis, so this is 0. M2 is just M. R2 from here to here, this is R2. Let me call the gap between them a distance D. This is distance D. So R2 is 2D, right? M3 is M, R3 is 2D. So all of them added together is going to be 8MD squared. Okay. So I'm going to do B now. B, so it's M1, R1. Again, R1 is from here to here. From where 1 is to where the location of axis is really just R1 is just D. So MD squared. R2 is also D, right? R3 is also D. This is R2, this is R3. R2 and R3 are both D. So it's going to be 3MD squared. I C, if you rotate everything relative to C, is M1, R1 squared plus M2, R2 squared plus M3, R3 squared. R2 is 0, R3 is 0, right? Because you are now at the center of the rotation, don't have any level arm. But R1 is 2D, so M2D squared. So it's 4MD squared. So you can see that this one is the biggest, this one next, this one is the smallest. RA is the biggest, C next, and the smallest is B. Okay, so B is the correct answer. Okay. Like we did previously, if you have a bunch of particles rotating, you simply just add them up. If you have a uniform distribution, you need to do the integral. And I'm going to show you the different cases for different shapes. Like I said, most of the time, the shapes that these rotational inertia is already calculated. All we need to do is refer to them and use them. So the first case is a ring or a cylindrical shell. And that is the same as a point mass. The total mass M times R squared. And why that is? Well, because all of the masses are all at the distance, same distance away from the center. So if you break this ring down into little m1 r, it's at a distance r away. Little m2 distance r away. You break them down, they all are at the same distance. So it's really just the entire mass times r squared. So rm r squared. But what about a filled disk? If you fill this in, and that's become 1/2. It actually end up to be less than mr squared. Does that make sense to you? That a filled disk has a smaller rotational inertia than a ring if they're all with the same mass m. So this one is 1/2, which is smaller than what it would have been for a ring or a shell. Does that make sense to you? Does that intuitively make sense?
Yes,
And why is that?
because with the solid cylinder, the mass is kind of everywhere, I guess you could say. It's on the outer edge, but it's also towards the center as well.
Yes, very good. So here, the mass is not all at the same distance r away. Some of the masses, actually most of the masses are at a distance shorter, right? Here is shorter, here is shorter. So it's going to overall average to be smaller than for the ring. Very good. The rotational inertia for a hollow sphere is 2/3 of mr squared. The rotational inertia for a solid sphere is even smaller than a hollow sphere for exactly the same reason. It's 2/5 of mr squared. And if you compare this one with this guy, again, it doesn't have all the bits of the matter, which is from, if you compare this with the ring, I'm sorry, it's small, again, smaller than a ring because not all of them have a distance r away from the center. All of this can be derived by doing integration. We're not going to do the integration. I'm going to show you a more of a simpler example for a one-dimensional case for a bar. So if you know how to do the bar, and you could attempt try to solve the other ones, but it's not really required. You just need to know uh, qualitatively why they're smaller than the rest. So let's try to do a rotational inertia for a long rod. But before we do that, let's try to set it up. We have an overall mass M, which is uniformly distributed over length L. The mass inside a short element dx is given by which of the following choices? Okay, so we want to know this little mass dn, and how is it related to dx is the question. Okay, so
DM is equal. Oh wait, I'm sorry. Are we answering this?
oh yeah, I'm going to open the breakout rooms.
Okay.
Okay, 10 more seconds if you haven't voted already. Okay, any more votes? All right, if not, I'm going to go ahead and close it. All right, I'm very glad that this is one of the, I believe we've done some of this before, right? I'm glad that you chose the correct answer is m over L times dx. So you can do this by looking at the proportion entire rod with mass m, entire length with mass L, length L. You're taking a small chunk of it, small distance. So what is the mass that's contained in the small distance is m over L times dx. Or you can view this quantity as sort of a mass density, right? The mass density of a rod is a total mass over the total length, sort of a linear line density of the rod, right? So it's a density kind of, yes. To have that, we can calculate this rotational inertia. So let's do this. The rotational inertia for a rod is you sum up all the little masses times that each of them have a distance that are away from the center. So here we have to be careful and specify relative to which rotational axis we're talking about. There are two ways usually of how this is, but not only two ways. You can rotate it relative to the center and rotate the rod this way, or you can rotate the rod relative to one end, right? So here we're gonna do the center first. From the center, you can see that they all at a distance x away from the center. This random little chunk is at a distance x away. So r become x times dm. dm is m over L dx. So you're doing m over L x squared dx. This integration, the limit is from where? From negative L over 2 to L over 2 if this is 0 from this center, right? From negative L over 2 to L over 2. So this becomes m over L. The integration of x squared is 1/3 x cubed from negative L over 2 to L over 2. If I plug in the numbers, I get m over L 1/3 L cubed over 8 plus L cubed over 8 minus the minus, two minus signs. So here is a plus. Here you get 1 over 12 ml squared. Oops, sorry. So relative to the center, the rotational axis for a rod is 1 over 12 ml over ml squared. Relative to, let's do the relative to the one end. So I relative to one at the end is m over L x cubed x squared dx, but from 0 to L. The integration limits to change, right? Is relative to this is from 0 to L. Then you get 1 over 3 ml squared. So you can see that relative to which axis you actually get different results. Does it make sense that relative to the end is bigger than relative to the center? Does that make sense to you? The rotational inertia, if you were rotating the rod relative to the end, is bigger than rotational inertia if you're rotating it toward the center. Yes, because one of them is harder to rotate, right? The one you're rotating relative to the end is harder because you're putting the masses at a higher distance away from the center. It's harder to rotate those bits of mass. Very good. Okay. Sorry, we did this. We have another one that's a disk. So now to calculate the disk, let's try to set things up. Again, can you find the little area of a thin grain that's living inside a disk? And we call it with a radius r away from the center with a thickness of dr. Okay. So you can again go ahead and discuss for a couple minutes and then we can do the calculation when you All right, so 10 more seconds if you haven't voted already. All right, so let's take a look. I'm gonna go ahead and close it. We want to find out the little area of this thin ring. It looks a little weird to calculate, but there's a trick that we can do. You can probably get rid of some of the obviously wrong answers by looking at the dimension, right? So if you know this is the area, we know that it has to be length squared, unit is meter squared, right? If you look at this one, r squared is already meter squared times the dr, you get a cubed, meter cubed. This one gave you a meter to the power fourth. So you can exclude some of the wrong answers by looking at dimension analysis. So that's just sometimes also a useful way to find an answer. Okay, so let's say, how do we calculate it? Well, this thin ring, if you make a little cut, like use a scissor and cut it and expand it, what does it become? It becomes a very long rectangle, right? So the thickness is what? Is dr. And the length, that's how long this ring is, how long the ring is. This is circumference. The circumference of the ring with a radius r is what? It's 2 pi r, right? So this, you can expand this ring into a long rectangle, and that is going to be, the area is going to be 2 pi r, that's the length times the width, which is dr. So B is the correct answer, okay? So now we have the area, we can calculate the rotational inertia for a disk, r squared dm, which is a generic expression. So what is dm? dm of this little ring is the density sigma times dA. Density is going to be mass over area. Earlier we did line density is mass over length. Here is mass over area, right? Mass over the entire area of the ring, of the disk. So the density is what? Is m. Area for a disk is pi r squared. dA is this 2 pi r dr. Okay, so that's my dm, right? Makes sense? You can get this relationship by doing a proportion as well. So for an entire disk with a total area pi r squared, for little disk with an area of dA, which is 2 pi r dr. So dm is pi r squared times 2 pi r dr, which you can still get this result if you don't use the idea of the density. Okay, just like what we did with the rod. Okay, so this is your dm. Okay, so now I'm going to do, so let's cancel some of these. It's going to be 2m over r squared r dr. And di is going to be, okay, so r is a variable, right? Each of these little m is at the distance r away from the center, and r changes from 0 to capital R. So it's r squared times another r dr. Now this is a constant from 0 to capital R, right? Okay, so 2m over r squared is your constant. You integrate r cubed dr, which is 1 over 4 r little r to the power 4 from 0 to r. Okay, we're almost done, almost there. So that's going to be 2m over r, 1 over 4 capital R to the power of 4. I'm sorry, I need an r squared here, mistake. Okay, what does this become? This becomes 1/2 m r squared, right? So that is the disk. That's the one that we have talked about. This is, and that this is how you calculate it, right? All right. Okay. So that's how a disk works. And you can see that you never really had to derive. It's nice that if you know how to derive, But in this course, when I give you a question that asks for rotational inertia, I will always give you the rotational inertia for that particular shape. But you have seen two examples. One is a rod, one is a disc, and you know how to do it, right? So here is a list of all the other formulas for ring, mr squared, for disc, 1/2 mr squared, for hollow sphere, 2/3, for solid is 2/5, for a rod about the center is 1/12. Again, today we also did the rod about the end, toward one of the end is 1/3 ml squared. So that is all the list that you may encounter in rotational motion. Okay. Next class, we're going to talk about the parallel axis theorem. Is that if you do have two different axes, just like you had for the rod, and how you find, if you know one, how do you find another? So for example, for the rod, if we already know what is at the center for the, and you shifted the axis to another location, you can use parallel axis theorem to figure it out without having to do the calculation all over again. Okay, but it looks like we did finish everything we want to cover for today, and this is a natural stopping point. I'm going to stop right here. So today we have discussed how to calculate torque, how to calculate rotational inertia, and after we discuss the parallel axis theorem for different axes for calculating I, we are ready to put everything together to do Newton's second law for rotation. We use this to do a lot of problems. Torque equals I alpha. Okay, so that will be the topic for next week. Next Thursday is going to be our exam day. So I want to let you know that I'm adding an office hour on Monday from 3 to 4. Again, we have our regular office hours on Wednesday from 3 to 4. Okay, so I encourage to come and ask questions before the midterm. So Monday and Wednesday. So for those who are not here today, I will go ahead and send out an email announcement on Blackboard so that everybody will know. The exam is on the 15th. That is a Thursday. Yeah, Thursday, the 15th. Okay, but if you encounter any problems or questions when you prepare for the exam, make sure you come to the office hours. That is next week. Would I be open? I do plan to have my computer open, but because I have may have another class, so I might be a little bit late to my regular class hours, but I do plan to have my computer open. Yes, so if you, for some reason that you open up your regular class Zoom and I'm not here, you simply leave me a chat and wait for me a little while or shoot me an email because I am coming from another meeting. Okay. All right. Oh, that's all for today. Thank you, everyone. We'll see you all next week. Okay.
Thank you, Professor.
Thank you, Professor. See you next week.
See you. We have.
Thank you, Professor. Have a great weekend.
Thank you.
Thank you.
Thank you.